Welcome to the elementary synthetic geometry-based Introduction to Inversion of the Real Plane with respect to a circle course, episode 4, lecture 4, in which we will prove the next three theorems numbered 6, 7, and 8, and in which we will solve the next four problems numbered 6, 7, 8, and 9. And if you recall, in the previous lecture, we solved a number of interesting problems in which we were given the circle of inversion, which means we were given the center and the radius of inversion, and we were asked to recover the positions of the inverse images under the different scenarios of the power of inversion, positive and negative. And in this lecture, we will solve the complementary problems in which the inverse images will be given to us, and we will be asked to recover the remaining parameters that identify a circle uniquely, that is either the center of inversion or the radius of inversion under both positive and negative powers of inversion. In the problem number 6, we're given two distinct points, the point A and the point A prime, such that both of these points are distinct from the unknown to us yet, mystery and sought after center of inversion, which we traditionally designate with the uppercase O, and the point at infinity. We're also told that these two distinct points are the images of each other under the inversion of the parent plane with respect to a circle whose center is unknown and the length of whose radius r is given to us in this problem. That means that the distances of the given points A and A prime from the unknown to us yet, mystery and sought after center of inversion O are locked into the relationship that we captured in condition 3 of definition 1 that is shown over here. The product of these distances is equal to the square of the radius of inversion, and under these conditions, when the power of inversion is positive, using nothing but the Euclidean tools alone, a straight edge and a compass, we're asked to recover the location of the center of inversion O with absolute certainty and correctly. And it should be understood that precisely because this course is based on synthetic geometry, what we're given in this and all the other problems that we'll come across in this course are the geometric objects themselves, not their coordinates, but the objects themselves. That means that in this problem, we're given two distinct points, A and A prime, each of which is distinct from the center of inversion that is sought after in the point at infinity. And that means that we are effectively given a line segment whose length I designated with the lowercase a, that is delineated by the given points A and A prime. The fact that the radius of inversion in this case is also given means precisely that we're given yet another line segment shown over here whose length precisely matches the length of the radius of inversion r, and it is perfectly legal and valid manipulate precisely this line segment that corresponds to the length of the radius of inversion and the line segment whose length I designated with the lowercase a, and that is delineated by the given points A and A prime. And under these conditions, we're asked to come up with an algorithm that uses nothing but the Euclidean tools alone, a straight edge and a compass that will precisely recover the location of the center of inversion under these conditions with absolute certainty and correctly. And as we explained in season 1, episode 2, we recommend that you practice mathematics correctly. As soon as you understand and comprehend the technical essence of the problem statement, we suggest that you put this video on pause, walk away from the computer, try to solve this problem correctly and on your own, and then come back and compare your solution to ours. That is right. What you saw just a second ago was a messy brainstorming session, and this is precisely what happens in the first instances once we understand the technical essence of the problem that we're trying to solve, and our mind begins to race in search of a solution. We try this, try that, we fail, we try again, we fail, we try again, and so on. We go in a cycle until we succeed. And arguably, this is the most fun stage of solving problems, which means that if you do not genuinely enjoy this messy, chaotic, and sometimes haphazard process, then you're doing something wrong. But in our case, where exactly do we begin solving this problem and how do we attack it? On this channel, we dedicated the entire season and then a little bit for dedicated study of the most popular problem-solving approaches. One such problem-solving approach that we studied in a dedicated manner in great detail is called reverse order. And this problem-solving approach is quite popular in constructive problems in geometry, and not only in constructive but in other problems too. And the essence of this problem-solving approach amounts to the following. We begin the search for a solution of our problem in the solved state of that problem. And what does it mean that the state of this problem is already solved? Well, that means that the sought after material, and here we're asked to find O using nothing but the Euclidean tools alone. So the center of inversion is not known, and that means that somehow, we do not know how yet, but somehow that center was located, and right now we are looking at it. Here, however, we have to step carefully because we need to first figure out what are all the possible locations of the mystery and sought after center of inversion. Well, here we use the first condition in the problem number 6 because we're told that the given distinct points that are distinct from the center of inversion and the point at infinity are the inverse images of each other under the inversion of the parent plane with respect to a circle, the length of whose radius is given, and the power of inversion is positive. So the first condition that we capitalize and the first bit or unit of mathematical information that we need to squeeze to our advantage is the following. These 2 points are the inverses of each other. And what does that mean? Well, according to condition 1, definition 1, recall this. The points in question must be what? They must be collinear. They must belong to one and the same straight line. So out of infinitude of points in the parent plane, we now zoom in to just one straight line. The point whose location is sought after the center of inversion, the point O, must be located somewhere on that straight line. Okay, that is very good. We used that bit of information, but what else are we told? Well, we're told that the power of inversion in this case is positive. So how do we extract actionable mathematics from that bit or from that unit of mathematical information? Well, we go back to our definition, and in definition 2, we remember we stated what? That the power of inversion is positive if and only if both points under consideration are located on the same side of the center of inversion. And what does that mean? Well, that means that we are not told which of these 2 points, A and A prime, is pre-image and which one is the image. We are not privy to this information. So in this case, we have to assume that one location for the center of inversion, and here I show the, let's say, given information in blue and the sought after information will be in red. That means that the center of inversion can be located over here. Does that location satisfy the definition of positive power? Yes, it does, because in this case, both points are located on the same side of the center of inversion. Is that it? Is that the only legal potential location of the center of inversion? If we think about it, then we will realize that no. We know for sure that this point cannot be located in between the given points because the power of inversion is positive. In the next problem where the power of inversion will be negative, that will be the case. But here in this problem, the power of inversion is positive, and that means that the set of points that is located between the given points is out of question. It cannot house the center of inversion. That means that the only other choice we have, the only other option, is that the center of inversion, O, can be located on this side. And does this location satisfy the definition of the positive power of inversion? Yes, it does, because if we assume for a moment that this here point is the center of inversion, then the given inverse images, the given points, are located what? On the same side of the center of inversion, so everything is good. So now that we assumed that the problem has been solved and now we're staring at a solution in a solved state, according to the reverse order problem solving approach, we begin unwinding the steps in the reverse flow of time, so to speak, this way and then this way and then this way and then this way somehow, and then arrive from the solved state to the original unsolved state. And the theoretical idea here is that this heuristic template tells us that the very process of traversing this solution path in reverse order may give us hints for the construction of the traditional or the forward flow of causality solution. And this is exactly what we want. So now if we are given the point O and the 2 images over here, then what fundamental approach can we take? This is a synthetic geometry based course. We're not going into introduction of coordinate systems and coordinates and the apparatus of analytic geometry, but that still does not mean that we cannot use a little bit of algebra. So here is a fundamental idea in approaching to the search for the solution of this type of problems. Our workhorse definition, in addition to other conditions, of course, but the workhorse definition of inversion of the plane with respect to a circle is captured what? Algebraically. We still have a formula over here. The product of 2 distances is the square of a certain quantity. So that means that first we want to solve this problem, or try to solve this problem algebraically. Can it even be done? Now, if we can solve this problem algebraically, then the second step will be to see if we can translate the algebra of the solved problem into the language, into the geometric language of synthetic geometry and the language of the Euclidean tools alone, the language of the operations that we are allowed to carry out using nothing but a straight edge and a compass. To that end, we have a little bit of combinatorial variation already going on. You guys can try to solve this problem by naming the unknown that is different from mine. Here I actually solve this problem both ways. We can take the distance from the mystery point O, the center of inversion, to the nearest point to be x. And here, for demonstration purposes, I'll do it the other way. I'll take the distance from the center of inversion to the opposite, to the farthest point, to be precisely x. We will designate it x. This is where algebra enters the picture. Now, if that distance from the center of inversion to the opposite point is x, and the distance between the points A and A prime that is given is A, then what is the distance between the center of inversion and the closest point? Well, that distance right here, this distance will be what? That distance will be x minus A. And we now go back to our workhorse formula, and what do we state already in terms of the material that we introduced? Well, the product of these distances, x minus A times x, must be equal to the square of the radius of inversion, r. And that quantity is given to us. In some sense, we can take it to be given to us algebraically, and it is given geometrically. We are given a line segment whose length precisely matches the algebraic, if you will, form of that data, the length of the radius r. And now what do we do? Well, this is where the algebra, the underlying algebra of the problem comes in. We try to unwind this mystery equation and try to solve it. So from here it follows what? From here it follows that if we open up the parentheses, we will have what? X times x is x squared minus a times x minus a times x. We carry r squared to the other side, to the left-hand side of the equal sign, minus r squared is equal to what? Is equal to 0. And what do we see? Well, we have a traditional quadratic equation, or more technically, more pedantically, an algebraic equation in one variable, x of order 2, over the field of real numbers in this case. And how do we solve this equation? Well, we will not be trying, there are other ways to solve this equation, for example, using the so-called Carlisle circles. That quadratic equation can be solved purely geometrically, and perhaps I will put an episode or two about that, but here we'll just cut to the chase and we'll solve this quadratic equation in a traditional way, and we will write down the formula right away. This will be what? Minus the coefficient attached to the first power of the unknown divided by 2. This will be a divided by 2, and then plus minus square root of what? The square of the coefficient attached to the first power of x. And then that whole thing is divided by 2. But if we bring in the 2 from under the square root into it, then the power of 2 will what? Will double, and we will be dividing a squared by 4. So here we can write down as follows: 8 over 2 squared minus 4 times the coefficient attached to the most senior power, which is 1, times the free-floating term, which is minus r squared. Minus times minus is plus, 4r squared divided by the 2 that came in from the denominator comes down to plus r squared. And On the one hand, we have solved the problem purely algebraically. Why is that? Well, the magnitude A is known to us. This is the distance between the given points. And as far as the line segment is concerned, as a geometric object, we're given that object. Dividing any given line segment in two equal parts can be done completely with Euclidean tools alone, with a straight edge and a compass. That can be done. It can be done over here as well. We know how to multiply. We know how to multiply any two quantities geometrically with Euclidean tools alone. Here we have a square, which means that what? R times R, we can multiply line segments. We know how to do it as long as the line segment of unit length is given. We know how to add line segments, we know how to subtract them, and we know how to compute the square root, or how to construct a square root with Euclidean tools alone. So now we understand that there is a hope, there is light at the end of the tunnel, and now we need to carry out precisely this step to which I referred earlier and translate the obtained solution in the language of algebra into the language of geometry, or more specifically into the language of straight edge and compass constructions. At this point, we are not out of the woods yet, and we still have a lot of fun ahead of us. In general, in more involved situations, the process of hashing the underlying algebra into the corresponding Euclidean tools alone solution can be quite challenging, and this is also a fun part. If you do not genuinely and thoroughly enjoying this type of work, then you are doing something wrong. This is the genuine fun, this is the genuine joy, this is where we exercise our wits, our improvisational and creative abilities. And here, on the one hand, some students who are not very savvy with this type of work will say, Roman, look, yes, we know how to constructively cut a line segment in two. We know how to constructively multiply any two line segments, provided that the line segment of unit length is given. We know how to constructively or geometrically add, subtract line segments. We know how to construct a square root of a line segment. This is all fine and dandy. We can do this, but oh my God, this is a lot of tedious and boring work. And these people will be right. On the one hand, that is the case, but this is precisely where mathematics comes in, because at its core, mathematics is built around an improvisation within the narrow band of technical constraint, but it is still an improvisation and the exhibition of your creative abilities. And I keep saying on this channel that mathematics is an art of telling a story. That is correctly also, but that doesn't mean that the underlying story has to be boring. That story can be exciting, it could be lively, and it could be sprinkled generously with lots and lots of creativity, and this is exactly what we do. Let's step back for a moment and look at the result that we obtained over here. We're given technically a line segment of length A. This is the line segment that is delineated by the given distinct points that are different from the center of inversion point at infinity. We know all that. What does our formula that we obtained over here algebraically tell us geometrically? Well, geometrically, now that we begin to translate the geometry, the algebra into the underlying geometry, tells us that the distance from the sought after center of inversion to the outer, let's say, inverse point A prime is partitioned or assembled from what? From two entities, from two quantities, if you will, from two line segments. One line segment is 1/2 of the given distance between the distinct points, and we know how to cut a line segment in half. So we know how to cut this guy in half. Let's say we found this point. This distance is equal to this distance. The angle over here is right. So this is our favorite perpendicular bisector. So we now look at x as what? A over 2 right here. This is this distance. Plus what? Plus this scary looking thing. But if we think about it, then we will realize that that thing is not as scary as it comes across at first. What do we really have over here? Let's think about it. Sum of squares and the square root of it. So what geometric theorem comes to mind? Many students know it as the Pythagorean theorem. This is also known as Euclid's Elements Book 1, Proposition 47. If I'm not mistaken, this is the very last proposition in Euclid's Elements for Book 1. He completes his Book 1 with this proposition, number 47. And that means that what we're given over here actually is the hypotenuse of a right triangle whose sides are known to us essentially, are known to us geometrically. One such side is what? Is the line segment of length r. And is it given to us? Well, let's take a look. Definitely, yes, it's given to us. We're given the line segment that matches in its length the algebraic, if you will, representation of the radius of inversion, which is just a real number. And we know how to obtain the other leg, the other side of this right triangle. This is precisely 1/2 of the distance that separates the given distinct inverse images of each other. And this hypotenuse, let us designate it. Let's say, for example, if you guys can see, it will be in orange. It will be in orange. That distance is this guy right here. Do you see that? This is what is going on. So that means, how do we translate this idea into the underlying idea over here? Well, we're already given 1/2 of the distance between the given points. So this is our side right here. This is given. Wonderful. What is missing? Well, if we can construct the radius r, then this distance right here, what will this be? This guy. Well, this will be precisely the square root of a over 2 squared plus r squared. You see this distance right here. And if we construct a circle with that distance, that circle will intersect our straight line L, which is technically given to us because the points A and A prime are given, and that circle will evidently intersect the given straight line L at 2 points, this point O and this point O, once we carry out the construction carefully. And this is precisely what it means to add and subtract one and the same line segment from the given line segment. If we take this part over here, this part as the given line segment, then the plus this quantity will be this line segment right here, and the minus, the bottom over here minus, will be the same line segment but counted or constructed in the opposite direction, and that will be the little bit that will stick out past the point A prime. And once we understand this, and this is actually, like I said, this is the fun. It's a process that's very fluid. It may be a little bit chaotic, but eventually all the chaos recedes, the clarity comes in, and with this admittedly messy process, but thoroughly enjoyable process, the solution actually evolves, and now we see it in our mind's eye and on paper. And the moment we understand what is going on and how all these things come together, we put together a solution that is already quite polished. And when the readers or the viewers of your solution look at it, they think, how did this come about? It's nice, crisp, it's polished, but what was the kitchen? What was the story? How are the details that saturated this solution came into existence? Well, that is how we reveal that process. This is one way. If you have another way to solve this problem, then share it with our community. The comment section is open, and perhaps the only question that some of our students have is, how do we construct this? How do we obtain this distance over here r? Well, that is quite straightforward. We're given the line segment, which I designated with the lowercase a, delineated by the given distinct points, the inverses of each other. We cut this line segment in half. We call this bisector B. We construct the perpendicular, see the perpendicular straight line through either one point. You understand, due to the symmetry, it doesn't matter, through one point. Then we snap a circle centered at one point, let's say this one, of which radius? Of precisely this radius is given to us according to Euclid's Elements, Book 1, Proposition 2, if I'm not mistaken. The Euclidean compass has memory. Once we open it up to measure one distance, we can carry this distance without closing the compass. The Euclidean compass has memory. We carry it over here, we snap a circle, we cut this distance, we snap another circle, and that's it, game over. This larger circle that will be centered at this point, but which will have which radius? Precisely this radius. Will intersect our line on which the points O, A prime, and the center of inversion sit at two distinct points, and either of these points will play the role of the sought after center of inversion. Game over. So now the way we prepare, let's say in a mock scenario, our work for publication, if you will, we clean up all this mess and we put together a nice, shiny, polished algorithm that solves the problem at hand. Which is, given the distance between two distinct points A and A prime, which are the inverses of each other under the corresponding inversion of the plane with positive power. As a step number one, we construct a straight line through these given points A and A prime. That straight line is shown in yellow, designated with L, step number one. Step number two of our algorithm: bisect the given line segment delineated by the points A and A prime with a perpendicular bisector B, perpendicular bisector to L, such that the point B that belongs to both the straight line L constructed in the previous step and the perpendicular bisector B constructed in the second step is equidistant from the points A and A prime as captured over here. The distance between the points A and B is the same as the distance between the points B and A prime. Step number three, construct a perpendicular P to the straight line L through actually any of the given inverse images through the point A or A prime. It doesn't matter here for demonstration purposes. I put the point A, but you can also do the same thing through the point A prime. Here that straight line is shown in orange. It's called P, perpendicular to L through the point A. This is a step number three, step number three, step number three, step number two, step number two, step number one, step number one. Step number four, shown over here, construct a circle, give it any name you like. I called it S, that has the point A chosen in the previous step as the center and R as the radius. And how do we do that? Well, we open up the Euclidean compass to the distance between the points that delineate the line segment that is equal in length to the given radius of inversion r right here. We carry to the point A and snap that circle. We do not really need the entire circle in all these constructions. The entire objects are rarely ever needed. We only need the intersection points. That circle S centered at the point A with the radius r will intersect the straight line P that we obtained in the previous step at 2 points. S intersects P at 2 points C and X. We do not care about the second point. We only need one. Here, for demonstration purposes, I picked that point to be C. We named it C. And the fifth and the final step, 5, we construct a circle. I called it sigma, that is centered at the point B, and that has the radius. The second argument to this notation is the distance between the points B and C. The distance between the points B and C is this distance right here. That circle, sigma, on the fifth step will intersect the straight line L that we constructed on the first step as shown over here. Sigma intersects L at two distinct points O and A prime. O and O prime. That are the points sought after. In other words, in this case, the solution is not unique, but still 2 points located with absolute certainty and correctly according to our fundamentally 5-step algorithm. But if we will actually carry out the constructions with more primitive steps, there will be more steps. But for a proof why this algorithm is correct, I will leave this proof as an exercise to the audience. You should be able to do it on your own, but again, put this video on pause, walk away, and try to generate this proof on your own. I will highlight the steps for a proof. They are quite straightforward. They're more than straightforward. The given distance, remember that we designated the distance from the center of inversion, let's say this one, O, and A prime is x. That distance, x, can be assembled from what? The distance from O, let's say, to A prime, likewise from O prime to A. It doesn't really matter which one we pick. This distance right here, at the risk of messing things up, this way or this way. You see, this way. So that distance can be assembled which way? Well, this is 1/2 of A, 1/2 of A, 1/2 of A, plus this distance. But this distance is this distance, BC. And what is the distance BC? Well, plus square root of A squared over 2, or A squared over 4, or A over 2 squared, plus R squared. This is how our construction went. And now we simply do the math. Carry the term A minus 2 over. X minus A over 2 is equal to square root of A over 2 squared plus R squared. Square both sides. X squared minus AX plus A over 2 squared is equal to A over 2 squared plus R squared. Cancel, cancel. X squared minus X is equal to R squared. Factor X out. X times A minus, sorry, this will be one copy of X. The X will be here, so this will be X minus A is equal to R squared. This is the product. This is the workhorse formula of inversion. So this distance times X minus A times this distance is precisely R squared. Collinear, same side, positive inversion. You bring this proof home, and that is how we solve the problem number 6. And now that we understand how things work when the power of inversion is positive, we will take on the next problem where the power of inversion will be negative. In the problem number 7, we are essentially asked to do exactly the same thing that we were asked to do in the problem number 6, with the exception that this time we will assume that the power of inversion is negative, as shown with the minus sign in red in the upper right corner of your screen. That is, we're given two distinct points, A and A prime. Both of these points are distinct from the center of inversion and from the point at infinity. These points are the inverses of each other. In other words, the distances from the mystery unknown to us yet and the sought after center of inversion O to these points are locked into the following relationship. Their product is equal to the square of the radius of inversion. The radius of inversion is also given. That means that we are given two line segments. One line segment that designates the distance between the inverse images, between the points A and A prime, and another line segment that precisely in length matches the real number, the strictly positive real number, to which we refer as r, that is the radius of inversion. And under these conditions, assuming that the power of inversion is negative, we're asked to find the center, the location of the center of inversion, or using nothing but the Euclidean tools alone, a straight edge and a compass, and we need to come up with an algorithm that is basically a finite number of steps, following which or carrying out which we will locate the position of the center of inversion with absolute certainty and correctly. Again, here is another opportunity to deal with a messy and a chaotic process of searching for a solution of a given technical problem. As we explained in the previous segments, if you do not really thoroughly and genuinely enjoy dealing with uncertainty, with the mess, with the chaos, then you are doing something wrong. This is the fun part, the fun stage in solving a technical problem. And we already explained how these types of problems can be solved in the previous segment using the so-called reverse order problem solving approach, in which we begin a search for a solution of this problem by assuming that the given problem was solved somehow. How it was solved, we do not know and we do not care, but we assume that the problem has been solved, and then we try to unwind the steps from the solved state to the original unsolved state. And the little bit of theory that goes with this heuristic template claims that reverse order journey may help us generate the traditional forward flow of causality solution. And in this case, we can do the following. Using the fact that the 2 points are the inverses of each other, we put these 2 points and the sought after center of inversion O onto one and the same straight line. L, we already know from the previous problem, from the solution of the previous problem, that this will be most likely the step number 1 in our algorithm. Then we use which fact? We use the fact that the power of inversion is negative. That means that the only possible locations for the center of inversion is somewhere in between the reverse images, in this case A and A prime. And again, the very light combinatorial variance over here already kicks in. We can designate different material with X. Here I will, for example, let's say, switch gears a little bit and designate the distance from the point O to the point A as x. That means that the distance from the point O to the other point, that is the inverse image of the first one, will be what? Will be a minus x. X, a minus x. Using the workhorse formula, the condition 3 of definition 1, we translate our algebraic and happy geometric mix over here of the unknown material with the known material into this equation. We open up the parentheses, x times a minus x squared. We carry r squared over to the left-hand side of the equal sign. We obtain this equation. We multiply it through by negative 1. We obtain the following equation, x squared minus a times x plus r squared equals 0 this time. This is technically an algebraic equation in a single variable, x of order 2 over the field of real numbers. Its solution is shown over here. It's a over 2 plus minus square root of a over 2 squared minus r squared. All this material is obtained in a straightforward way. I explained in detail in the previous segment. This is what you are expected to obtain too if you go with these designations. And now that we managed to solve this problem algebraically, we step into another messy and quite often challenging but still fun stage of solving a problem, of translating the underlying algebra of a solution into the geometric steps that use nothing but the Euclidean tools alone. In this case, when the power of inversion is negative, as shown with the red minus sign in the upper right hand side corner of your screen, then the square root formation represents what? Well, here, instead of the sum of the squares of two line segments, as we had it in the previous problem, problem number 6, in this problem we have a difference. So what does that mean geometrically? How do we translate all this scary looking and potentially horrible expression over here into the underlying geometry? Well, in this case, that distance represents a side of a triangle where the hypotenuse is known. The hypotenuse is known as a over 2, and the other side is known r. And the remaining side of this triangle, of this right triangle, this side right here, precisely represents this term, you see? That is the one key observation that will help us translate the underlying geometry of the solution into the Euclidean tools-only algorithm. Again, we go back to our algebraic representation of a solution, and we may forget about minus or plus depending on what is more convenient for us. Let's say we take the minus sign here first because it's easier to deal with. For example, for some people, some other people, it will be easy to deal with the plus. It doesn't matter. So x is the distance between the point O sought after, the center of inversion, and for example this point A is represented what is half of the known distance between the inverses of each other, the points A and A prime, and we know how to cut a given line segment in half. So if we cut this line segment in half with the perpendicular bisector B that is perpendicular to the straight line L that passes through the inverses, such that the point B, where B and L intersect, is equally distant from the points A and A prime. That represents this A over 2 term. So this is A over 2 right here. And then x is what? Is A over 2 minus, let's say minus, we'll play with this side, with this corner, minus this itsy bitsy spider, this guy right here. You see this piece, and what is this piece? Well, that piece, that line segment, is precisely the side the other side of a right triangle whose hypotenuse is what? Is a over 2, because we subtract from the square over here, and the other side is equal in length to r, the radius of inversion. So if we construct, for example, through this point a straight line that is perpendicular to L through O, and onto that straight line we put our radius r as shown over here, then this distance right here will be a over 2, and that is precisely the missing link, so to speak, is this line segment that is represented algebraically over here. You see, this is how these things work. So now the final question is this. We constructed this straight line for a visual demonstration of where our Euclidean tools algorithm is going through the point O, exercising our wishful thinking. But we know that the location of the point O is not known. So in our algorithm, we cannot do that. So how do we address this issue? Well, we simply parallel translate the radius r, or fundamentally, we do what we can do. And what can we do in this case? Well, we can bisect our line segment that is delineated by the inverses in half. That we can do. That's the yellow bisector B. On that straight line, we can construct a circle whose radius is exactly r. It will be here, for example, somewhere. We construct the circle. That circle will intersect the bisector at two distinct points, but we choose one. And then we simply translate this point. How? By drawing a straight line that is perpendicular to B and is distant precisely r units away from L this way. And that straight line will intersect what? What else can we do? Well, it will intersect the circle that will be centered at the point B, but whose radius will be exactly what? Exactly a over 2. This guy right here. This point and this point. Of course, on my drawing it looks horribly out of place, but you understand. So this point will be this one. Drop a perpendicular, bam, bam. This is our points O, problem solved. Now that we understand how the solution is developed, again, we throw all this messy and chaotic stuff out and we present a solution that is polished. Which is, as a step number 1, we construct a straight line named L through the given points A and A prime. That straight line shown in blue over here, straight line L, step number 1, step number 1, step number 1 algebraically, step number 1 geometrically. Through the given inverses, one straight line shown in blue called L, step number 1, step number 1. Step number 2 is an evident one. We construct a straight line B that is perpendicular to L in such a way that, pedantically speaking, the straight line B intersects the straight line L constructed in the previous step at a point B, such that the distance from the point A to the point B is the same as the distance from the point B to the point A prime, as shown over here. That straight line geometrically shown in yellow over here, that straight line B number 2, number 2B, number 2B geometrically, algebra, geometry. Step number 3, now that we obtain the point B that is equally distant from the points A and A prime, we use it as the center of the circle. Let's say it's named S, that has the radius R that is given to us. We open up the compass to the distance that is R, carry it over to the point B, snap a circle. I show the circle only partially. Step number 3, step number 3, step number 3, step number 3. Here partially, we only need one little piece little chunk of that circle S centered at B with the radius R. Technically, that circle S will intersect the perpendicular bisector B at two distinct points, C and X. X we don't care about, we need only one. For demonstration purposes, let's say that is the point. And now we, in the step number 4, remember the parallel translation into the, remember our wishful thinking, parallel translation. We construct the straight line named lambda that is parallel to the straight line L through the point C, precisely through the point C here. Step number 4 in orange, lambda parallel to L through the point C, through the point C. All these steps are completely doable with the Euclidean tools alone. Now, step number 5 is the construction of the circle named sigma that has the point B as its center and a over 2 as its radius. We already know how to do that. Point B as the center. Open up the compass to the distance, for example, to the point A prime or A. Snap a circle, call it sigma. Step number 5. Algebra of the step number 5. Geometry of the step number 5. The circle shown in white. That circle will intersect the straight line lambda constructed in the previous step at two distinct points, D and E. D and E. E and D. E and D is the intersection of lambda and sigma that has B as its center and A over 2 as its radius. Step number 5, algebraically in notation, geometrically, shown over here. And we are pretty much done, because now in 2 steps we bring it home with the step, for example, number 6. We construct a straight line called P sub A, perpendicular to L through the point D. This straight line shown in green over here, P sub A, 6 algebra, 6 geometry. Straight line, PA, perpendicular to L through the point D, right here, through the point D. Step number 7, the algebra. We construct a straight line PA prime, also perpendicular to L, but through the point E. Or if you want, we can do perpendicular to lambda. It doesn't really matter. So we can say L or lambda. I'll put in lambda over here. It doesn't really matter because lambda and L are parallel. But the final step, we construct the straight line P sub A prime, let's say perpendicular to lambda through E, and that straight line will intersect the point L at the sought after point A prime, and the straight line P sub A will intersect the straight line L. P sub A will intersect the straight line L at the point O, and these 2 points are the sought after points. Again, the solution is not unique, but the location of the centers of inversion is recovered with absolute certainty and correctly. And how do we know that? Well, again, I will leave this proof as an exercise to the audience. This is more than straightforward. It's very straightforward way to observe that, for example, in my designation, that was the distance x, that was x, that was distance x. So what do we do now? We represent this, we assemble this distance x as follows. The distance from the point A to the point B is A over 2, and it is equal to x plus, what is this distance? Remember that this radius over here is A over 2. So this is what? This is square root of A over 2 squared minus, by construction, this distance, but this distance is this distance, and this distance is what? Is r. Exactly, r squared. And from here onward, we manipulate. We bring, for example, what? We bring A over 2 minus x to this side. That is equal to this horrible square root. We square both sides. We obtain A squared over 4 minus ax plus x squared is equal to a squared over 4. What is this? Minus r squared, a squared over 4, a squared over 4. Cancel out. Switch the material. Put r squared is equal to ax minus ax squared. Minus here disappears, minus here disappears. And then simply rewrite it as r squared is equal to x times a minus x, and voila. X, the distance from the point O to A is x, and A minus x, it will be this distance right here from O to the point A prime, because the entire distance is A, the distance between the points A and A prime, and this is our workhorse. The points are collinear in between, and so on. You polish the proof and you present it as a complete solution of the problem number 7. In synthetic geometry, if the location of the center of a circle and the radius of a circle are known, then such a circle is determined or defined completely. In the previous two problems, we recovered the location of the center of inversion, and in this problem and in the next we will do the same, but with the radius of inversion. As such, in the problem number 8, we're given two distinct points that are the inverses of each other under the inversion of the parent plane with respect to a circle whose center again is given, but the radius is not. And this is the objective of this problem, is to come up with the Euclidean tools only, a straight edge and a compass algorithm that will recover the length of the radius of inversion under the assumption that the power of inversion is positive. And again, our two distinct points A and A prime are both distinct from the center of inversion and from the point at infinity. And in this case, we are given the location of all 3 points of interest. These points are distinct because they are the inverses under the corresponding geometric transformation. That means that all 3 points are collinear, and because the power of inversion is positive, then that means that the center of inversion that is given this time is located on the same side with respect to both of these points, or conversely, the image points are on the same side of the center of inversion. And under these conditions, we need to recover the length of the line segment, that is the radius of inversion. We need to do it using the Euclidean tools alone, a straight edge and a compass. And again, we recommend that you practice mathematics correctly. The moment you understand the technical essence of the problem statement, put this video on pause, walk away, and try to solve this problem completely correctly and on your own, and then come back and compare your solution to ours. Here is one purely geometric way of solving this problem, even though some of our viewers can try to solve this problem in a different way, mostly algebraically, based on the solution of the problem number 6, where we designated some amount of information as unknown, then we constructed the workhorse relation, and here basically all the distances are known, so we need to extract the square root of the known quantity, and we know how to construct square roots with Euclidean tools alone. This is one solution, which is perfectly fine. Here is another that is purely geometric. Recall that in problem 1 and in problem 3, we were given a circle of inversion, which means we were given the location of the center of inversion, and we were given the radius of inversion, and then we were given one pre-image point, and across these two problems we came up with a solution that we later realized was not symmetric with respect to the location of the pre-image point relative to the circle of inversion. When the pre-image point was located strictly inside the circle of inversion, we carried out one set of steps, and when the pre-image point was located outside of the circle of inversion, we carried out similar steps but in different order, and then we managed to construct a solution that was symmetric with respect to the location of the pre-image point in reference to the circle of inversion. But this time, let us go back to the non-symmetric solution and try to recall how did we construct, let's say, the image of the point A that was located, let's say, inside the circle of inversion. Well, first we constructed the straight line through the points O and A through the center of inversion and the given pre-image point. Then we constructed a line that was perpendicular to the straight line OA. That straight line intersected our circle of inversion at two distinct points, out of which we only need one. We connected the center of inversion with that intersection point B, and then we snapped a straight line through B perpendicular to OB until this straight line intersected the straight line OA at the point sought after. That was our basic algorithm, and this straight line that is perpendicular to OB turned out to be what? A tangent to the circle of inversion that I designated with tau. This straight line is a tangent. Now let us step back a little bit and think about what can we do here in order to solve the problem that we're given under the positive power of inversion, recover the length of the radius of inversion. Well, here we can capitalize on the fact that if we try to reverse engineer this geometric solution, what will we have? We do not have in this problem the circle of inversion precisely because we do not know what the radius of the circle is. We are supposed to find it. So how can we, on the one hand, it may sound a little paradoxically, but how can we construct a tangent to a circle whose shape we do not know? Well, apparently we can. Let us think about it. This time, we're given the center of inversion, and we're given both points that are the inverses of each other under the inversion of the parent plane with respect to this circle, whose center we know, but whose radius we need to recover. So here, what can we do? Well, in our original solution, what did the line segment that connects the center of inversion and, let's say, outer point, what role did it play? Recall that the angle OBA prime here is what? Is right, because the straight line through the point B that is perpendicular to the straight line OB was what? Perpendicular, orthogonal. This line forms exactly right angle with the straight line OB. And that means what? That means that the line segment OA prime can play the role of what? A diameter of a circle that is constructed precisely on the line segment OA prime shown over here. And can that be done? Yes, of course, that can be done because we're given all 3 points. So now, reverse engineering our solution, we already see where things are going. So this process is not really that chaotic. It's not too messy. It's actually quite elegant in a way if we can zoom in on this idea right away. We know the distance between the center of inversion and the first image point, and between the center of inversion and the second one, and we know the distance between the inverses of each other also. But that means that we can cut the distance between the center of inversion and the outer point in half, obtain the point where that line segment is cut in half, use it as a center of a circle that uses the line segment O A prime as a diameter. So this circle will necessarily run like this. This circle will run like this. That circle can be constructed. And what else can be constructed? Well, we utilize the point A prime. Now is the term for the utilization of the point A. What can we do over here? Can we construct a straight line that is perpendicular to the straight line that we call L usually and passes through the point A? Yes, we can do that all day long. And that straight line, let's say we'll call it P for perpendicular, will intersect our helper circle, sigma, let's say, at two distinct points out of which we need one. This will be that point, the point B. So at this point, we can actually draw a straight line that passes through the points A prime and B, and that straight line will be a tangent to a non-existent circle. But we do not really need to do that, because the moment we intersect the helper circle sigma that uses the line segment O A prime as a diameter with a perpendicular to L through A, boom, we get our point B, and the distance between the point B, this distance right here, and the center of inversion is precisely what we are required to find. The length of the radius of inversion and the length of the line segment B O or OB will be precisely that quantity. That will be the length of the radius of inversion. Game over. So now, with our somewhat messy but not too messy and not too chaotic reasoning, which basically comes down to reverse engineering our solution of the problem 1 and the problem 3 and taking advantage of what can be done in order to precisely locate the point that belongs to the circle of inversion. And once we have that point, the distance from that point to the center of inversion, which is known, the game is over. We solve the problem. And now we take all these manipulations and all these ideas, we polish them, and we present them as a complete algorithm. That is, given the center of inversion and two points that are the inverse images of each other under the inversion of the parent plane with respect to the circle that is centered at the given center of inversion, and the assumption that the power of inversion is positive, here is a Euclidean tools only, a straight edge and a compass algorithm that will recover the length of the radius of inversion. First, we construct a straight line L through the points. In this case, it actually can be any points. I use the center of inversion and the other point. It could be A prime here or A prime here or A, which is located also anywhere. The idea here is to construct a straight line that houses all 3 points of interest as is stipulated in condition 1 of definition 1. Here is this blue line L, step number 1. Step number 1, step number 1. As a step number 2, we have to be careful. We need to bisect with the straight line B that is perpendicular to L. What? We need to bisect a line segment that is delineated by the center of inversion and the outer point that is the inverse image of the other one. So however we want to designate that, this is what we should designate over here, because this is the important part. We want to take the point that is not between the center of inversion and the other image point. That is basically the idea. In this demonstration algorithm, we take the point O, the center of inversion, and the point that I designated as A prime. And we bisect the line segment O, A prime in order to obtain the point B, such that the distance from the point B to the point O, the center of inversion, and the outer point A prime is one and the same. Once the location of the point B is known, we use it as the center of the circle sigma, the step number three, the circle sigma centered at the point B that has the radius as the distance from the point B to the point O, or from the point B to the point A prime, it doesn't matter. That is the radius for the circle sigma. This circle is shown in white. The step number three geometrically, the step number three captured with symbols. Step number four, we construct a straight line named P that is perpendicular to the straight line L constructed in the first step through the remaining point, the point that is in between the center of inversion and the other inverse image that is given to us, whatever that point is, A prime or A, it doesn't matter. In my demonstration algorithm, they came out to be the point A. And it will so happen that the straight line P will intersect the circle sigma constructed in the previous step at two distinct points, C and D. Step number four, captured in symbols. Step number four, captured in geometry over here. This is the green line named P, step number four, that is perpendicular to the straight line L and passes through the point that sits in between the center of inversion and the other inverse image. That straight line P will intersect the circle sigma at two distinct points, D and C, and technically the game is over. Our algorithm terminates at this point. We do not really need to draw anything else because the distance from the point O to either the point C or the point D thus constructed is precisely the length of the radius of inversion sought after. Game over. Algorithm terminates. All the steps that are described over here, 1 through 4, can be carried out with Euclidean tools alone. And for a proof, again, the proof at this point is so straightforward that I will leave it as an exercise to the viewer. You should go back and pull up the records for our the way we solved problem 1 and the way we did all the previous work, as a matter of fact. But here, as a hint, if you have any trouble constructing a proof that this algorithm is correctly and precisely recovers the distance r, again, we go back to three right triangles. The triangle O, let's say C, A prime. Why is this triangle right with the magnitude of the interior angle at C being right? Well, that triangle is right because it subtends a diameter of the circle sigma, and the circumference angle in the diameter of any circle is right, as shown over here. Now, from that right angle vertex, we construct a height of the triangle that falls precisely on the hypotenuse OA prime at the point A. This is how we obtained all these points. And now we have two more right by construction triangles, the smaller triangle OAC and the smaller right triangle CAA prime, as shown over here. And what is this? This is a typical setup for Euclid's, technically Euclid's book 6, proposition 8. Look it up on the internet. It's available free of charge. The idea is that these two smaller right triangles, the triangle OAC and CAA prime, are similar, and both of these two smaller triangles are similar to the parent triangle OCA prime. That can be proven by basically chasing the angles. We already did that in the previous lectures. You can go back to your records and look over there. But which triangles will you need over here in this case for the proof of this that this algorithm is correct? Well, you'll need this distance over here, which is part of this triangle, of the smaller triangle, OAC. And you will need the distance OA prime, which means that you need the entire parent triangle. In equiangular triangles, as Euclid puts it, or in similar triangles, the lengths of the sides that subtend equal angles are in the same proportion. So you construct this proportion and it will turn out that the length of the side OA, for example, relates to the length of the side OC in the smaller triangle OCA in the same way as the side OC in the larger triangle OCA prime relates to what? To the hypotenuse OA prime, and that is how your relation will pop up. In other words, with this similarity of these triangles, you will basically arrive at the following ratio. You will say that the distance OA over the distance OC will be the same as the ratio of OC to the hypotenuse OA prime. Over here, the cross product will be equal to OC squared, and that is precisely the definition of what? The definition of the radius of inversion, because the points OA and A prime are all collinear. The points A and A prime are located on the same side of the center of inversion, as the positive power of inversion requires, and that will complete your proof. And now that we understand how things work when the power of inversion is positive, in the next problem, the problem number 9, we will solve the similar problem, but by assuming that the power of inversion is negative. That is right. In the problem number 9, we're asked to do essentially the same thing that we were asked to do in the problem number 8 in the previous problem, but under the assumption that the power of inversion this time is not positive, but is negative, as is shown with the red minus sign in front of the square of the radius of inversion. That is, in the problem number 9, we're given 3 distinct points, and just by their mutual juxtaposition, it is evident that the center of inversion must be located in between the 2 points that are the inverse images of each other. Why? Precisely because the power of inversion is negative, and we know that the power of inversion is negative if and only if the center of inversion is located strictly in between the images of each other under the corresponding inversion. Under these conditions, we are asked to invent a Euclidean tools only, a straight edge and a compass algorithm that will allow us to recover the length of the radius of inversion with absolute certainty correctly and in a finite number of steps. Here again we have an opportunity to deal with something that is messy and chaotic, because we do not really have any formulas to shuffle, any symbols to plug and chug. We have to use our power of creative imagination in order to submit the local material to our will and solve the problem. To that end, on the one hand, it is always possible to algebraically extract the square root from both sides of our favorite by now workhorse relationship that locks in the distances between the inverse images of 2 points in the plane. On the right hand side of that result, we will have the length of the radius r. On the left hand side of that result, we will have plus minus square root of the product of two distances. All the distances are known. We know how to construct a product of two line segments, and we know how to extract a square root of a given line segment using nothing but the Euclidean tools alone, provided, of course, that we're given a line segment of unit length. And in this case, we're not given that line segment. In some sense, if we wanted to, we could have introduced it into a problem statement. But on this channel, this is not who we are. This is not what we do. We do not look for mundane and boring, in some sense, tedious solutions. We always want to spin the given local material creatively. And to that end, we go back to the solution of the problem number 2 and the solution of the problem number 4, where, as you remember, we were given already a circle of inversion with negative power, and in the problem number 2 we were given the pre-image point that was located strictly inside of the circle of inversion, and we were asked to recover its image that was located outside. And in the problem number 4 we were given a pre-image point that was located strictly outside of the circle of inversion, and we were asked to construct its image that is located inside the circle of inversion using the Euclidean tools alone. We'll solve the problem. We actually noticed that our Euclidean tools algorithm in this case came out to be symmetric with respect to the location of the pre-image point in reference to the circle of inversion. If we recall that construction was based precisely on the fact that we already are given the circle of inversion. We refer to this circle traditionally as lowercase c. It doesn't matter, just for definitiveness. That circle is shown in white. Our first step, we remember, was to connect the center of inversion and the pre-image point, wherever it was, and construct a straight line L. That was our first step. The second step was to construct the perpendicular straight line P that is perpendicular to L at the center of inversion. And that line number 2 shown here on board in yellow. That straight line P, we understand, will intersect the circle of inversion C at 2 distinct points, out of which we need only one. I designated this point at B. What was the third step? The third step was to connect the pre-image point with that point where the perpendicular to the straight line L through the center of inversion and the circle of inversion intersect. Notice how beautifully the symmetry of this construction works, because whether the pre-image point is located strictly inside or strictly outside of the circle of inversion, that construction works either way. If the pre-image point is located strictly inside of the circle of inversion, we connect that point with the point B, and we snap a perpendicular to that line segment through that point. Let's say this one. Conversely, if the pre-image point is located outside of the circle of inversion, we still connect that point with the point B, and we snap a perpendicular to that straight line through B. Either way, that perpendicular, this one or this one, intersects the straight line L at the sought after image point. Now, in our problem, if we would try to reverse engineer the construction that we came up in the problem number 2 and the problem number 4 creatively, what would we say? We would say that in this case, in our problem, we're precisely asked to find r. We're given the center of inversion, but we do not know what the radius r is. So in some sense, that circle becomes invisible. We do not know what the radius of that circle is, and we are asked to precisely recover the length of that radius. So what can we do? Can we construct the straight line L shown in blue over here as the first step? Yes, of course. We're given all 3 points, so in some sense this is a no-brainer. Snap a straight line through 3 given points, and precisely because these points are the inverses of each other, we know condition 1, definition 1, all 3 points of interest are what? Are collinear. They precisely belong to that straight line. So we can do that. Step number 1. Can we snap a straight line that is perpendicular to L through the center of inversion? Yes, of course, all day long. That point, the center of inversion, is given to us. So far, so good. As a step number 2 in our polished algorithm that is coming up, we understand, that will be the step number 2. We carry this one out. Now, in our solution of the problem 2 and problem 4, that perpendicular already intersected the circle of inversion at the point B. But in our case, we do not have that circle of inversion C. What do we do now? Well, we capitalize on the fact that in our solutions of these problems, the angle at the vertex B of the corresponding triangle was what? Was right, but by construction, we forced, in some sense, that requirement upon to the local material. Wonderful. Can we manufacture a right angle that looks like this and that has our image points as the legs of that angle? Well, the answer is yes, of course. If we make the line segment that is delineated by the image points, in this case, a diameter of the corresponding circle, game over. In other words, if we cut the line segment that is delineated by the given image points in half, let's say like this, and we will call this straight line B for perpendicular bisector, the angle over here will be right, the point over here will be ABC, let's say C, such that C, this point, C, that point, that these distances are the same. And then if we construct a circle, and I'm about to destroy the beauty of this construction over here by drawing by hand, what will we have? We will have a circle that has this line segment as a diameter, and that circle will have no choice but to pass through the point B that belongs to what? That belongs to the perpendicular bisector P, and it belongs to our helper circle, that we'll call that circle sigma, let's say. And that point at the same time, you see, it belongs to at least 3 beautiful geometric objects. That point will belong to our circle of inversion, the mystery circle of inversion C, which, let's say, we'll show in dashed style, which right now we do not have. And our idea is to actually, in some sense, reconstruct it. Because now we will have a point that belongs to all these 3 objects. It is important that it will belong to the circle of inversion C, which means that the distance from the center of inversion to that point will be precisely R, and this is exactly what we're asked to find. And that is the, in some sense, creative analysis or creative brainstorming. It was not too messy, but it was quite manageable. But this is how we hone in onto a solution of a given problem, by basically reverse engineering our solutions that we generated for the problem 2 and the problem 4. And as long as we understand that the helper circle over here can be constructed precisely because we're given the distance between the points that are the images of each other under the corresponding inversion of the plane that is centered at the point O, then that problem becomes solvable in a very straightforward manner. And now that we understand where does this solution come from, we can polish it and present it as a ready and finished algorithm. And before we deep dive into that algorithm, please allow me to observe that in various settings, be it in a forum or in a book, when such algorithms or overall solutions are dumped onto the audience, then the only question that comes up in the minds of curious travelers is one and the same, and invariably that question is, where did that come from? Well, we know where did that come from because we showed in the public setting the analysis and the steps that led to that algorithm. Now we pack away, remove all the mess and all the chaos from our creative analysis of the problem, and we present the polished steps, which are given three distinct points, the two images of each other that are the inverse images of each other with respect to the inversion of a plane that has the center at the point O with negative power. We recover the radius, the length of the radius of that inversion with Euclidean tools alone in a finite number of steps with absolute certainty and correctly as follows. As the step number one, we construct a straight line that houses all the points. Here I show the points A and A prime, let's say the two inverses of each other with respect to the corresponding inversion, but it should be understood that precisely because we are given 3 points that satisfy these conditions, these 3 points are collinear to begin with, so constructing that straight line is straightforward business. So symbolically, step number one shown over here. Geometrically, step number one is shown over here. L, blue line that houses all 3 given points. The center of inversion, and in some sense we do not really have to be given the names of these points. All we have to be told is that the power of inversion is negative, and we can be given actually 3 anonymous points by their mutual juxtaposition. We know that the point in between the other two is the center of inversion. And how we name the other 2 points, let's say the outer points, it doesn't really matter. In my demonstration, I named the left point A and the right point A prime. In your case, you can swap them around and the solution, the essence of the algorithm will be the same as such. Step number one, straight line through all 3 given points shown in blue. Step number one. Step number two, bisect the line segment that is delineated by the 2 points that are located on either side of the in-between points, of the in-between point. That is, snap a straight line B perpendicular to L such that the distance from the point where these 2 straight lines intersect is the same from the point B to the point A and from the point B to the point A prime as shown over here. Usually I do not want to throw too much symbology on this course. There is no need to do it, but pedantically, if you want to be more formal, this is what you will write, that you construct a straight line named B. It is perpendicular to the straight line L constructed in the first step, and the straight line B is constructed in such a way that it will intersect the straight line L at the point B such that the distance from that point B to the points A and A prime is exactly the same. Game over. Step number two symbolically, step number two geometrically. We do not really need the whole straight line, we just need a little piece of it. And here it is, step number two geometrically, step number two symbolically. Step number three, now that we did all the preparatory work, we construct a circle, sigma, centered at that point B that has the radius, precisely that distance from B to A and from B to A prime. Step number three symbolically, step number three geometrically. Here is the circle in white named sigma. I do not have the room here, but technically you could have written here exactly that. Sigma is the circle that has the first object is the center, the second one is the length of the radius. we stick the needle of our compass here and snap a circle, which can be done again with Euclidean tools alone. Step number 3, geometrically. Step number 3, symbolically. And the fourth and the final step, we construct a straight line named P perpendicular to L through the center of inversion. We designate the center of inversion as O traditionally in this course, just for definitiveness. It doesn't have to be. We can name it anything you want, but instead of writing center of inversion, we just write the symbol O. That is the step number 4 in symbols. Step number 4 in geometric objects. It's a straight line P perpendicular to L at this through the center of inversion. That straight line is shown in green over here. That straight line, technically, it's enough to construct it in such a way that it just gives us one point, but if we want to, we can snap that straight line in such a way that we physically get it to intersect the circle sigma, shown in white, that we constructed in the previous step at 2 distinct points, C and D. And this is what I captured over here. The perpendicular P intersects the circle sigma C. The circle sigma that we constructed in the third step at 2 points, C and D. Technically, you can write C is not equal to D. For example, you could, if you want to be overly pedantic, you will say C is not equal to D, and such that the distance from the point O to the point C and D is one and the same, and it is precisely the distance sought after. So in these 4 global steps, which will unwind into slightly more primitive steps of drawing circles and snapping straight lines, we accomplish the task that we set out to accomplish in a finite number of steps with absolute certainty and correctly. This step number 4 terminates our algorithm. This is the end of our algorithm. Let's say we can put it this way, designated with a square. And now for a proof. Again, the proof of the fact that this algorithm is correct is so straightforward. I will leave it as an exercise to the audience. You should be able to generate that proof on your own. But if you do have any trouble, then as a hint, what you want to do here is the following. Let's say I'll use this is an incredible simulation of a straight edge. Let's say we want to connect the points C, let's say this one, or you can do the point D, and the point that is given to us as one image point, and we want to connect C with the other image point. I usually try to not refer to them as A and A prime because they can be any ones. This point can be A and this point can be A prime, it doesn't matter. But precisely by construction, because this line segment subtends what a diameter of the circle sigma, the angle, the magnitude of the angle is C is what is right. And from the right angle vertex, we drop what a height onto the corresponding hypotenuse of the right triangle. In this case, it will be AC A prime. And like I told you guys many times, Euclid Elements, book 6, proposition 8. This is the proposition. Basically, we proved that proposition essentially in our in the previous lectures, where we showed that the parent triangle ACA prime, that is right, is similar to both of the smaller triangles, and these both smaller triangles are similar to each other. What are the smaller right triangles here? The smaller right triangles here are AOC and COA prime. Why do we pick those? Well, because these guys deliver precisely the distances that we need. On the one hand, we're told that because the points A and A prime are the inverses of each other under the corresponding inversion, we know that the distance between the center of inversion and this point and the distance between the center of inversion and this point is locked into this relationship. But here we need to say equal to, technically, let's say x squared. Temporarily we'll put x squared. Now the triangles AOC and COA prime are similar by angle, angle, angle. And how do the angles play out here? Well, let's designate them with different colors. Let's say with this color, with the green color, we'll designate this angle. What is the angle of the same magnitude in this triangle? Well, it's this one right here. See this one. And let's say this angle right here, I'll designate it this way, will be this guy. And the game is essentially over. The game is over because now we bring in book 6 proposition 4, if I'm not mistaken, if I'm not wrong, which says that the lengths of the sides in similar triangles that subtend the same angle are in the same proportion, where the corresponding sides lie opposite equal angles. So in this triangle, in the smaller triangle, how should we should cross-hatch it this way. Let's say this triangle. We'll need this triangle, and then we'll need this triangle. You see these two triangles. From this triangle AOC, what would we write? We would write that the length of the side AO, or let's say if we took it as a convention to write the center of inversion first, so the distance from the center of inversion to the first point relates to the distance OC. In the same way in which what is going on with the smaller triangle COA prime. Here, the side OA of the triangle COA lies against this red angle. In the triangle COA prime, which side lies against the angle of the same magnitude? Well, that side, OC. So this is what we'll write. OC relates to which side? The side that lies opposite the angle, the green one, this one. So that's the side OA prime. OA prime. And there you go. Cross multiply OC, the product of the distances from O to A and from O to A prime will be equal to OC squared. But in this case, OC squared is precisely the radius x. So this is exactly that. This proves our claim, and that proof completes the solution of the problem number 9. Before we begin discussing the proof of the theorem number 6, let us summarize what we have achieved so far. Across the solutions of the first 9 problems and the proofs of the first 5 theorems, we managed to prove that all the interesting material that characterizes or deals with the inversion of the real plane with respect to a circle is constructible with Euclidean tools alone, with a straight edge and a compass, with absolute certainty, correctly, and in a finite number of steps. That is, we showed that we can accomplish such a construction for the image of a given point with both powers positive and negative, the center of inversion with both positive and negative powers, and the radius of inversion, again with both powers positive and negative. And this is an interesting fact in its own right. And now, in the next lecture, we will begin studying how the inversion of the real plane with respect to a circle acts on slightly more complex geometric objects on straight lines. But before we do that, we will finish this lecture with 3 small theorems that will come in handy in the future. That is, in the theorem number 6, we claim that the point A prime, that is the image of the pre-image point A, under the inversion of the real plane with respect to a circle C that has center at the point O and radius R, is unique. That image point is unique. Again, we suggest that to derive the most academic benefit from taking this course, the moment you comprehend the statement of the theory, put this video on pause, walk away, try to generate your own proof for this theorem, and if your proof you think is in some sense better, shorter, more crisper, more elegant, more beautiful, by all means share it with us and then compare your proof with ours. Now, for a proof of this theorem, we go back again to our trusty workhorse relation that algebraically, in some sense, defines the heart and the soul of the geometric transformation that we're studying right now. And we observe that according to condition 3 of definition 1, the distances from the center of inversion to our points of interest are locked into the following relationship. Their product is equal to the square of the radius of inversion. Now let us designate this distance over here that controls the location of the image point with respect to the center of inversion as x. Then this relationship will be rewritten which way? The distance from the center of inversion to the pre-image point times x is equal to r squared, and now we pull some algebraic magic, if you will. We rewrite this equation as follows: the distance from the center of inversion to the pre-image point, a times x minus r squared, is equal to 0. And now we put the algebraic goggles on and we claim what? This is technically an algebraic equation in a single variable, x, over the field of real numbers, because we're studying the inversion of the real plane. And it turns out that even going deep into the theory of groups with the corresponding alternating group A1, this group turned out to be solvable. That equation always has a solution, and that solution is unique. That solution is unique, provided that the distance from the pre-image point to the center of inversion is not 0. That root of that equation is unique, provided that, of course, the distance OA is not equal to 0, which in our case translates that the point A is distinct from the center of inversion. And we agreed that this is the case by our convention. We say that the center of inversion is taken into the point at infinity, which we remember is what? This is the planar image of the north pole of the Riemann sphere under the corresponding stereographic projection. And conversely, the point at infinity is taken into the center of inversion under the inversion of the plane with respect to a circle, and so on. And in our case, this is precisely the situation. The pre-image point is distinct from the center, and that result over here shows that the distance that we marked as the distance from the center of inversion to the image point is unique. Now, in general, of course, the fact that the distance is unique in the plane, that means that that distance x from the given center of inversion, if this is x, the set of points that honor that distance is what? Is technically, remember our discussion earlier, a circle is not a disk and a disk is not a circle. So this equality and the fact that this distance is unique means that in general we have technically uncountably infinitely many points such that this condition holds. There's only one distance, and there are many places in plain English where that can happen. But remember our condition 1 for definition 1, that all the points of interest must be what? Must be collinear, and out of all the possible points that honor that condition of being constant and unique, one and the same, not more and not less, but precisely that. We evidently, when a circle and a straight line intersect, they do so at two distinct points, but we already know that for each case we have precisely the meaningful definition, the positive power of inversion or negative power of inversion, and that fixes the location of the point A prime with the corresponding power of inversion uniquely. And that precisely means that the claim of this theorem is true. Under the inversion of the real plane with respect to a circle, the image point is unique regardless of the power of inversion, positive or negative. And that completes the proof of the theorem number 6. The theorem number 7 claims that any even number of inversions of the real plane with respect to one and the same circle and one and the same power carried out in succession applied to the same point A takes that point into itself. Technically, the grown-up mathematicians will say a composition because that is what takes place or unfolds when we apply two transformation in sequence one after another, and the result or the output of the previous transformation becomes the input for the next transformation. So the official word is composition, but in our case we will state it simply that any even number of inversions of the plane with respect to one and the same circle, one and the same power applied to one and the same point takes that point back into itself. Any even number is captured as 2n symbolically, where n is a strictly positive whole number, 1, 2, 3, 4, 5, 6, 7. So the number of consecutive inversions will be 2, 4, 6, 8, 10, 12, and so on. But it is evident that for a proof of this theorem, it is enough to cover the case when n is equal to 1, and consider what happens to the point if we flip it twice or invert it twice in the same circle with the same power, and then if the even number that is given to us is greater than 2, we simply repeat the same proof any finite number of times that is equal to n into n representation of that number. Now, the proof of that theorem is not very complicated. You should be able to generate that proof yourself. Again, we recommend that you put this video on pause, walk away from the computer, think about it on your own, come back and compare your results to ours. If your proof is even better in some sense, more crisp, more elegant, more beautiful, more enlightening, we're always looking to learn. The comment section is open. Share your idea, share your beautiful idea with our community. But one proof that can be generated for that theorem is basically amounts or rides on unpacking the relevant definitions. That's all it is. So for two consecutive inversions of one and the same point in one and the same plane and in one and the same circle with one and the same power, that is important, because when we do several things in a row, we can bring new material in. We cannot do that over here. If we start inverting the given plane with positive power, we always keep reflecting that plane with positive power. And if we decide to carry out 2n consecutive reflections of the plane in one and the same circle with negative power, then we always do it with negative power. We never flip, we never change. Positive power, negative power, positive power, negative power. Always one and the same power. So let's say under the first inversion, the point A is taken into the point A prime, and under the second inversion, the point A prime is taken into the point A prime prime. Then what does that mean? Well, for now, we assume that the point A prime is distinct from A, and we work in that under that assumption and see what is going on. Now, from the first assumption, we know that according to our condition 3, definition 1, we have the distance from the center of inversion to the pre-image point times the distance from the center of inversion to the image point A prime must be r squared. That much we know. But at the same time, we know that the similar relation must hold for what? For this pair of points, A prime and A prime prime. So here we write the same result. The distance from the center of inversion to the point A prime times the distance from the center of inversion to the point A prime prime must also be r squared, because remember, we're carrying out an even number of inversions with respect to the same circle, or in some sense fixed circle. And what does it mean that the circle is fixed? The circle is fixed when the center of that circle, O, is fixed in one and the same place, and the length of its radius is fixed. Nothing varies in between. Now, here we just proved in Theorem 6 that this point, the image point, that much we know, is what? It is unique. It is one and the same. So when the power of inversion is one and the same, regardless of that of the flavor of that power, positive or negative, that point will be unique. And the fact that that point is unique from this two relations, it follows what? We express it in terms of the locally variable available material. The distance from the point, or from the center of inversion to the point A prime, is what? Is r squared divided by the distance from the point, from the center of inversion to the point A. This is result from this, from the left relation, and from this relation over here we express this distance in terms of this distance will be what? R squared divided by the distance from the center of inversion to this imposter point A prime prime. So far, the position of that and the position and the identity of that imposter is quite fluid. But what do we see over here? The radius of inversion is one and the same. So from here it follows that as far as distances are concerned, we just proved that the distance from the center of inversion to the pre-image point must be exactly the same as the distance from the center of inversion to the imposter, A prime prime, to the point A prime prime. Again, the equality of distances in the plane means that we have potentially uncountably infinitely many candidates for the points that will satisfy this. But now we fix the power of inversion, and what do we say? Let's say the power of inversion is positive. The power of inversion is positive. We know that according to our condition 1, the points O, the center of inversion, A and A prime, must belong to one and the same straight line. I will give it a fancy name, lambda, just to imprint it onto our minds that these points are collinear by definition. By the same definition, we also have it that the points, which ones? The points O, A prime, and A prime prime must be also collinear, let's say temporarily lineal, but we know any two distinct points which are fixed define what? A unique straight line. So if the points O and A prime belong to a straight line, then the points here, O and A prime, in this relation must also belong to the same straight line. So the point A prime prime, in fact, must also belong to one and the same straight line lambda. And what does that mean? Well, in general, regardless actually of what the power of inversion is, we just prove that all the points O, A prime, and A prime prime are collinear, and they belong to one and the same straight line lambda. Now, when the power of inversion is positive, the points O, A, and A prime are located on the same side of the center of inversion, and so must be the points A prime and A prime prime. So what does that mean? When the power of inversion is positive and this condition holds, well, the points A and A prime are on the same side somewhere. Let's see, somewhere over here. Like this is, let's designate this as a center of inversion, O. The center of inversion O. This is the point A. This is the point A prime. They are on the same side of the center of inversion O here. And the points A prime and A prime prime also must be located on the same side of the center of inversion, but this relation must hold true. Well, the only conclusion we can draw over here is that precisely in this case, the point A prime prime must be identical, must be indistinguishable from the point A, from the original point. So in some sense, we take the point A, we throw it into its image A prime, and then we apply the same inversion to the point A prime, and that point A prime is taken back into the point A itself. Now again, there is not much complicated material, just careful deduction based on our definitions, and that exactly what it means to unpack the definitions. Now, when the power of inversion is negative, when the power of inversion is negative, then what happens? Well, then the point O, the center of inversion, must be in between the points A and A prime. It must be in between the points A and A prime, the pre-image and the image point. Same exact requirement must apply to the points A prime and A prime prime. The center of inversion O must be in between the point A prime and A prime prime. So somewhere here, there must be a point A prime prime. But we already have again the same relationship. The distance from the temporary imposter A prime prime to the center of inversion must be the same as the original point A. So what does it mean? Well, it means that these 2 points actually are one and the same. So the point A is exactly the same as the point A prime prime. And this is it, game over. Under both powers of inversion, that is the case. And if this proof is valid and correct for just 2 consecutive inversions, then it is evident that it is correct for any more even number, because we simply replay the same proof for the next 2 copies and the next 2 copies and the next 2 compositions and so on. And that completes the proof, as long as everyone in the audience understands and everyone in the audience is on the same page that the power of inversion is fixed for the duration or for the length technically of this composition. Any even number of consecutive inversions of the same plane with respect to the same circle under the same power takes the original point back into itself. And now that the proof of this theorem is complete, we can also observe that the theorem number 7 can be formulated slightly differently but equivalently. And how? Again, put this video on pause, walk away, think on your own, come back and compare your ideas to ours. An equivalent way to state the theorem number 7 is the following. If the point A prime is the image of the pre-image point A under the inversion of the given plane with respect to a circle C centered at O with the radius R and the chosen and fixed power, Then conversely, the point A is the image of the point A prime under the inversion of the same plane with respect to the same circle under the same power. Now, in this case, we can say that the points A and A prime are symmetric with respect to the inversion of the real plane with respect to a circle C centered at the point O and the radius R. The final theorem of this lecture, the theorem number 8, claims that the inversion of the given plane with respect to a circle named C, whose center is located at the point A and that has the radius R with negative power, as is shown over here with negative power, is equivalent to inversion of the same plane with respect to the same circle, but with positive power followed by, this is the sign for composition technically in grown-up mathematics, but we will say positive power followed by the rotation of the parent plane, PL, parent plane, about the center of inversion O by pi radians, and because of this particular angular measure, it doesn't really matter clockwise or counterclockwise. So one more time, in order to make sure that we all understand what the statement of the theorem number 8 is. The inversion of the given plane with respect to a given circle with negative power is equivalent to the same inversion with positive power followed by the rotation of the parent plane about the center of inversion by pi radians, or in plain English followed by basically half a turn. That is all there is to it. Now again, the location of the pre-image point for a proof of this theorem, again, use this as an opportunity to practice mathematics correctly. If you understood what the premise of this theorem is, put this video on pause, walk away, try to generate your own proof, then come back and compare your idea to ours. But here the proof of this theorem will unfold in the same way regardless of where the sample pre-image point A is located in reference to the circle of inversion C. It can be located strictly inside, it can be located precisely on the circle of inversion, it can be located strictly outside of the circle of inversion. Again, we understand that we take the cases when the sample point is distinct from the center of inversion and the point at infinity. For demonstration purposes, let us assume that a sample pre-image point shown in blue, A, is located, let's say, strictly inside of the circle of inversion. Then we know that in order to obtain that image with respect to the specified inversion, we carry out the following construction. We construct a straight line through the center of inversion and the pre-image point, snap a perpendicular, take the intersection point, connect it with the center, snap another straight line perpendicular to that radius or tangent. Boom, we obtain the point A prime shown in red. That is the image of the given point with positive power. Here, let us agree that A prime is the image with positive power. But we also know how to obtain the same image when the power is negative. We construct a straight line that is perpendicular to the line through OA, through the point O, this one. The intersection of that straight line with the circle of inversion give us another point. Connect the pre-image point with that point, snap a perpendicular, where that perpendicular intersects the blue straight line OA. Boom, gives us the image of the given pre-image point under the inversion with negative power. And that point I showed in green with the subindex n for negative, A prime negative an. Again, it may so happen that the point shown over here will be pre-image point, and then this will be the image point of this point. Then this image of that point with negative power will be located where? Well, it will be located on that side and inside of the circle of inversion. We know this due to the theorems and problems that we solved. But again, it doesn't really matter. Analytically, this problem, this theorem is proved in the same way regardless. Let us say for the positive power of inversion, we go back to our condition 3, definition 1, and we state what? The distance from the center of inversion to the pre-image point times the distance from the center of inversion to the image of that point with positive power is the same r squared as the distance from the center of inversion to the pre-image point times the distance from the center of inversion to the image of that point under negative power a prime n. That much should be understood by everyone. This is straightforward. Positive inversion, positive power of inversion, negative power of inversion. Same side of the center of inversion, in between the pre-image and the image, or vice versa. It doesn't really matter. What do we have here? Well, the pre-image point A is evidently one and the same point. That means that this distance and this distance can be canceled out because r squared here is one and the same real number. It does not change. Remember, all these things, the identity over here assumes that the circle of inversion remains the same this time. We play games with the power of inversion, but the circle of inversion is the same. So from here it follows that we have the distance from the center of inversion to the image of the point A with positive power is equal to the distance from the center of inversion to the image of our point with negative power. You see, this is the key observation. And again, analytically, what do we say? We repeat pretty much the same argument that we repeated in the proof of the theorem number 7. Remember that according to our definition, the points O, A, and A prime are all collinear. They belong to one and the same straight line. And here the fact is that this point, the center of inversion, is one and the same. The pre-image is one and the same. So these 2 points, if we go back to many of our proofs and solutions of constructive problems, what was the first thing we did? Well, we snapped a straight line through the center of inversion and the pre-image point. These 2 distinct points define a unique straight line. Let's say we will call this straight line lambda. So under the inversion with positive power, this must be the case. Under the inversion of the same plane, with respect to the same circle, but with negative power, we still have this thing that is called condition 1, definition 1. The 3 points of interest must still be collinear, but we have 2 points that are the same, the center of inversion and our original point A. That means that there is no room for play over here. Game over. There is no room to wiggle or no room to maneuver. The points O, A, and A prime must belong to the same straight line lambda, and that means that the point A prime n must belong to the straight line lambda, which is the same straight line to which the image of our pre-image point A prime with positive power belongs. What does that mean? That means that our points A prime, which is the image of the point A under the inversion with positive power, and the point A prime n, which is the image of our pre-image point A under the inversion with negative power, still belong to one and the same straight line lambda. This is very straightforward middle school type argument. There is nothing fancy or difficult to comprehend is going on here. So this information, this fact, combined with this fact, so these two facts together mean what? Well, they mean precisely the claim that we stated in the premise of the theorem number 8. That means that the image of the given point under the inversion of the chosen plane with respect to the chosen circle with the fixed center and the fixed radius, let's say r, can be obtained which way? Well, the equivalence means that in order to obtain the image of the given point with, let's begin with the negative power. With negative power, we can obtain the image of the given point with positive power and then rotate the plane, or rotate that point technically, about the center of inversion by pi radians. Again, more technically or constructively, that means drawing a circle. Let's call it the helper circle S. The helper circle S, lowercase s, that is centered at the point O and has this radius, OA prime, until that circle intersects the straight line lambda for the second time. For the first time, that circle will intersect our straight line lambda at the image point A prime with positive power. For the second time, boom, it will intersect the straight line lambda at a point which will be what? It will be the image of the given point under the inversion of the same plane with respect to the same circle, but with what? With negative power. So here we will say, let's designate it with the same color in green. We will say negative power of inversion, and here we will use red for positive power of inversion, just to make it painfully clear and not ambiguous. That is how we obtain the image of the given point with negative power. And conversely, if we construct the image of the given point under the inversion of the plane with respect to a circle, C centered in O with the radius R with negative power, then in order to locate the position of the point that is image of the original point with positive power, we simply rotate our negative power image around the center of inversion O by pi radians until that point lands exactly on the image with positive power of the point A. Again, technically that means constructing a circle S that has, let's write it down, the circle S has the center at the point O, and the radius of this point is either the point O A prime or O A prime N. Center, radius. Game over. Theorem proved. This completes the proof of this theorem. If you have any questions, the comment section is open. Ask away. If you have a better proof, then share your better proof with us. But this theorem actually establishes the fact that constructively the inversions of one and the same plane with respect to one and the same circle, but with positive and negative powers, are equivalent in the sense that is captured by the spirit of this theorem. And that means precisely that if we're given the image of a given point with positive power, then the image of the same point with negative power can be constructed algorithmically and deterministically in a finite number of steps. And we explain how by drawing this here circle until it intersects the straight line that connects the center of inversion and the given point. And conversely, if we're given the image of the point with negative power, we can always locate the image of the given point with positive power by drawing the same circle. And that is the sense in which the positive and negative powers of the inversion of the plane when everything else is fixed is equivalent. That is the meaning of equivalence, and we can use this theorem as both a theoretical fact and as a tactical device in the upcoming problems and theorems.